verify, according to the slope of the tangent line and the gradient, I will be able to see these two are indeed orthogonal. Okay? So I'm saying the tangent line, I'm saying the level curves are orthogonal to the gradient. Essentially, I'm saying they're orthogonal to the tangent lines, okay, because these are curves. So essentially, we're talking about if you draw a tangent line here, these two vectors are orthogonal. Know what I mean? Yeah? Okay. Gradient at this point is pretty easy to compute. All right? Gradient at this point is pretty easy to compute. And just look at this guy is fx and fy. Okay? So let's quickly get the answer here. So it's going to be minus x divided by 2 and minus 2y divided by 25. All right? So if I evaluate at this given point, I have to go pretty quick at this particular example so we can finish on time. So it's 2 square root of 3 and 10. It is equal to minus square root of 3. So I have a 20 divided by 25 is minus 4 divided by 5. Okay? So this is the gradient. So this is the gradient. But in order to compute the slope of the tangent line, I have to take a little bit effort here. First of all, that equation is saying 21 minus x squared divided by 4 minus y squared divided by 25 is equal to 14. All right? I want to compute the slope of the tangent line. In other words, I want to compute the y dy dx according to this equation. Sounds familiar? I want to compute the derivative dy over dx according to implicit function. What's the word I'm looking for? Implicit differentiation. If I want to compute the dy over dx, one way to do that, I can solve for y. I go y is equal to a function of x, and then I take the derivative. Another way, which is much easier, is to look at a big function f of x and fy, and then take the minus. Right? According to this, my fxy can be equal to, say, 21 minus x squared divided by 4 minus y squared divided by 25 minus 14, so it's going to be 7 minus this whole thing. Right? So I can make my fxy to be equal to this function. So dy over dx will be the partial derivatives of fx and fy. And I have a minus sign. Remember, you have a minus sign here. So it is equal to minus fx is equal to minus x divided by 2. And fy is minus y divided by 2y divided by 25. So in the end, what we have is, what is it? It is going to be minus x divided by y. I have a 2 and 25, and I have a 2 right here. So in the end, I have minus 25x divided by 4y. Okay? That's our derivative of y with respect to x from the implicit differentiation. If you don't want to take the implicit function theory, you can simply take the derivative with respect to x directly to this equation on both sides. You'll be able to get the same answer. Okay? You can take the derivative with respect to x. This one disappears. This one gives you minus 2x divided by 4. And y is depending on x, so you have 2y and then y prime. Right? So you can take the derivative with respect to x directly to this equation without even using the implicit differentiation. But these two are equivalent. These two are equivalent. So when I plug into the equation dy over dx, when my x is equal to 2 square root of 3 and y is equal to 10, is equal to minus 25 multiplied by 2 square root of 3 divided by 4 times 10. It's going to give me minus 5 square root of 3 divided by 4. Okay? So this is what I have. Okay, so sorry, I have to borrow 1 minute of yours. So if I have the slope of the tangent line to the level curve is equal to this guy, how do I verify the tangent line is indeed orthogonal to this gradient? Okay, if you have a slope of a tangent line, you want to assign a vector to that tangent line. It's going to be 1 minus 5 divided by 3 divided by 1. So basically, this is what I'm saying. If a slope of a straight line is this number, then the vector in this straight line will be exactly 1 minus 1 and the slope. Am I right? Mm-hmm. Slope is basically talking about if you increase x by 1, y will be increased by the slope. So if I want to assign a vector to this straight line, I'm exactly letting 1 and minus whatever you have, which is exactly the slope right here. So this is the slope. The vector will be exactly equal to 1 and the slope. This vector is not necessarily uni, right? It's not necessarily of the unit length, but it doesn't matter when I want to check orthogonal, right? So orthogonal just tell the direction. So amazingly, if I multiply these two by unit vector, I'm getting a minus square root of 3 plus square root of 3, and I'm getting a 0. So you can indeed verify it in a calculus way such that the gradient vector is indeed orthogonal to the tangent vector. So I won't be too quick for the last problem, but I hope you can look at your textbook or the lecture notes too.